Okay, so welcome back to this course. It's the last lecture we devote to that big first chapter. This one, which has very many things, all of them are important, and also a very good number of very interesting problems, exercises. We'll not have many exercises in what follows. But let's look at these because I left you with some rather difficult exercises. This is one. Find a bipartite graph that it is not isomorphic to a subgraph of any K-cube. Something that puzzled a friend here. How can we prove that something will not be a subgraph of any K-cube? Not only 1, 2, 3, 4 cube, but 1,000 cube, 1 million cube. Well, it is possible, as I show you. So two things to do. One, which is important, intuition. The idea of finding something which can be a solution. A second part, argument, reasoning, to prove that actually that is a solution, okay? Has anybody found a solution? Well, okay, we already discussed very briefly that, of course, as it is written here, if we just, since they just asked for a graph and they don't specify a simple graph, as I think you here, okay, and also another friend from outside found that if we put there two multiple edges between two vertices, that of course builds bipartite graph, but is not isomorphic to a subgraph of any K-cube. So please do what the author actually meant. So a bipartite simple graph that is not isomorphic to subgraph of an AK cube. This is difficult, and actually I went through all of the new edition. I've told you that this is the old edition of a book which was studied by whole generations of graph theorists. And then it was substituted by something for which you should pay, on the contrary, meaning a new version. And I went through this new version of the book, and I didn't find this same exercise. I hoped to see that they wrote a bipartite simple graph, but the exercise has disappeared, maybe because it's a bit difficult, as we are going to see. First, my solution, and it was also the solution of other people, so I think it is the simplest solution, maybe. This is it. This is clearly a bipartite graph. You see? Well, I don't want to put there colors because I'll use quite a lot of colors for something else. But this and this are in one set of the bipartition. This and this and this are build the other set, X and Y. Okay? So it's clearly a bipartite graph. And now I should try to show that no possible K-cube can contain this as a subgraph. And I don't like, as you have maybe noticed, I don't like proofs by contradiction, okay? Still, I don't see any other possibility than doing a proof by contradiction here. And my solution for showing that this is necessarily not embeddable into, not a subgraph of a K-cube is by saying, let's assume that it is actually a subgraph of a K-cube for some unknown K, okay? And let's see that we necessarily go to a contradiction, all right? So what we have is that we have here everything, even if we have k very big, 1,000, 1,000,000, but everything is played in 3, maybe 4 at the end, maybe 4, but let's talk about 3 coordinates. Why? Because if, let's start with these two. If these two vertices are are joined by an edge, it means that they, as k tuples of zeros and ones, are equal up to exactly 1 coordinate, where we have on one side 0, on the other side 1. Okay, so let's assume that we have a string of zeros and ones, and at a certain point, let's say at level I, at coordinate I, we have here, say, a 0. It does not, it's not so important to have here a 0 or a 1, because by permuting we would get all the other possibilities, okay? Let's assume that here we have 0, that same thing at position I. Here we have 1, okay? And all what follows is exactly equal in this and in this, okay? Otherwise, they would not be connected by an edge. This is the way we can think, even if k is unknown and very big, but how we can deal with this thing, okay? They know that if they are joined, then they differ by exactly 1 coordinate. So only here, before this string of I don't know how many zeros and 1 is equal to this one, and also what follows, which I'm going to depict also now, okay? So now we have to deal with this and this, okay? And so let's say that they have the same initial string. And so here, this has this, and in position I, we have 0, okay, as we have here, and we go on, say another string of I don't know how many symbols, and in position J, let's say that here we have 0, and here we have 1 in position J. Okay? And for what follows, they are exactly the same. But mind, here we must have that in position J, we have 0. Why? Because from here on, the string must be exactly the same that we have here. Otherwise, they would not be joined by an edge. Okay? And let's go on. And now let's talk about these two. Okay, this means that we have another unknown string. Okay, oh, sorry, let me first put here this string, this string. Here in position I must have 0. Here in position J, I must have 0, as we have here. In position K, we have 0 here, and we have 1 here. And here we must have 0. And here we must have 0 in position K. And then we have the same final string for all of them. Okay? So far, no problems. But look at what we have here. Okay? Here, what should we have? This and this must differ by just one coordinate, always because of the same reason, because they are joined by an edge. And so let's say that here we have same red string, and what about what we have here? And we must have the same blue string, the same green string, the same final yellow string. We must have here some numbers. Can it be a 1 here? If it were a 1 here, then we should have a 1 as 0. We should have a different number somewhere else, because we cannot have exactly the same total strip which we have here. Can it have a 1 here? It cannot be 0, this cannot be 1, 0, 0, cannot be 0, 1, 0, cannot be 0, 0, 1, okay? In order to be different from this of exactly, on exactly one coordinate, we should have here, sorry, we should have here 0, 0, and 0, okay? 0 for having something different from this, 0 for having something different from this, 0 for having something different from this, but then we would have the same, exactly the same string that we have here. This is not possible, because they would be the same vertex. So maybe we have a difference somewhere else, maybe we have a difference. Let me say that we have a difference here, where we have maybe a 1 here at the same position, here, say at position H, and we have a 0 here and the 1 here. No, why? Because then we would have from, say, from this to this, we would have two differences. One in this position and one in this position, okay? And so it's not possible to have whatever the length. It's not important that we have a very long K. After all, we have 3 positions, possibly plus 1, say 4 positions to look at, okay? And no more, because of the definition of edge here. So this is a solution. Think about it, because, as I told you, it's not an easy solution.
Oh. Yeah, Professor.
Tell me.
Is it really possible to draw something like this and find this graph just in 5 minutes, 15 minutes, really?
What do you mean?
I mean, I just thinking about that really simple solution that was a bipartite graph, which was not simple, around 2 hours. And as you said, just think 15 minutes, and it is really
no
hard
more than,
for me to.
yeah, sure, no more than that, because, as I said, this is a difficult problem, my friend. I repeat it for the K+1th time. It's not important for me that you solve these exercises. It's extremely important that you attack these exercises, that you try, that you put your mind and the tools that you already have at work for deepening inside into the problem. When you are deep into the problem and you think 15 minutes are a very long time. I know because I do physical exercise for actually Kung Fu, and my master says, okay, do the same thing, exactly the same thing for 10 minutes. And 10 minutes are desperately long if you do always the same thing. So 15 minutes for this exercise are very much, very long time. And okay, it's possible that you don't find the solution. I'm not competing with you. You are not competing with each other. All of us, we are trying to understand things, okay? And for understanding things, you must try to work. But I know that you yourself, you said you thought 2 hours, and 2 hours is too much. Don't
Yes,
try to live, have a walk with your face mask, of course, and eat a wonderful ice cream. I don't know whether you have as good ice creams as we have here in Bologna, but okay.
of course, I love it. I love it. But it is
Okay.
my characteristic that whenever I can't find some solution for a question, I will thinking over the night.
No,
I
no, no,
cannot.
no, no. Over the night you must sleep. Okay, promise.
For
All
sure.
right, all
Thank
right,
you. Thank
all right, my friend. Okay, so let's go to the next problem.
Excuse me, sir.
Please.
Would you please explain the diagram, these zeros and ones? I couldn't get how we can
Sure.
describe it.
Then, first, this is my proposal for the solution, this graph here, okay? X and X, Y as bipartition. So actually, every edge in the graph joins a vertex in X with a vertex in Y. So it is surely bipartite. We'll also see next a theorem which asserts also, tells us that necessarily this is bipartite. Anyway, it is clearly bipartite. Now the difficult thing is to show that no K cube can contain it, okay? The key for this proof is in the definition of the K cube, which says what vertices are, K tuples of zeros and ones, different from each other, of course, and what an edge is. An edge connects two vertices, that is, two k-tuples, if and only if these two k-tuples differ in exactly one position. Okay? So, for instance, my start was I take this vertex and this vertex, and these are, sorry, k is not meant to be the same k. Oh, maybe this is misleading. Okay, let's say L, position L. So my argument is, what about this k-tuple and this k-tuple? They must be absolutely equal apart from one position. What is this position? I don't know, but there is exactly one position where they differ. So I dumped this position to be position I. And in position I, we have here either 0 or 1, and here the other symbol. Okay? Let's say that here we have 0, and here we have 1. For all the rest of the k-tuple, we absolutely must have the same symbols. You see what I mean? Okay? And I
Yes, sir.
repeat, okay, so now I repeat the argument for this and this. So what should they have? That they are k-tuples, 1000 tuples, which differ exactly in one position. This position cannot be I, okay? Because I is already taken by this. I mean, here, if everything, all the rest is equal, here if we have 0, we have this, if we have 1, we have this. So the difference must be in some other position. Call it J, okay? In position J, we'll have on one side a 1, on the other side a 0. Let's say that we have 0 here, so we must have 1 here. And exactly in the same way, in position, yes, in a certain position L, I don't know which it is, but it is there, and it is different from I and J. In position L, I have here 1, here a 0, and everything else must be equal. Okay? So now what is left here is that I cannot have that it is everything equal apart from what? From these three positions? No, because then for being different in exactly one position from here, it should have 0 at position I. In order to be exactly different from one in another position, it should from this in another position, it should have 0 here, because here we have 1, and to differ from this, we must have 0 here, since here we have 1. Okay, but then if the red part, blue part, green part, yellow part of the big string are equal in all of these, then we would have that this vertex is exactly equal to this vertex. So let's assume that we have a difference somewhere else, say here in a certain position H, where here we have all zeros, and here we have 1, just to differ from this which has 0, but then it's not again possible, because then we would have two differences, because here we have a 0 in the same position. Let's put it. And here we would have a difference here and the difference here, so two differences, and then these two vertices could not be joined by an edge. Why? Because they differ in two positions instead of one. Okay, so this proves that it's not possible to have a K-cube in which we have this subgraph. Okay, let's go to this other one, but I have lost.
Subgraph has to differ from another subgraph for just one position.
What do you mean?
For definition.
Can you please take off your face mask?
A subgraph, position of a vertical graph.
No, a subgraph means that these are some vertices of, there is a K-cube, which has...
Bipartite subgraph. Bipartite subgraph. Bipartite subgraph.
This is bipartite.
Has to differ just for one position from incident vertices.
No. Why should it differ? You mean here and here? Yes. Sure, it is the definition of K-cube. The K-cube, I repeat, a K-cube is the set of all K-tuples of zeros and ones. Okay? Where each vertex is a K-tuple of zeros and ones, and two vertices are joined by an edge if and only if these two K-tuples differ in just one position. It is the definition that we have in the book, okay?
Thank you so much.
You're welcome. Let me take, I closed it silly. Okay. So now we had this problem, okay? If you have a graph, not necessarily a simple graph, okay? Any graph, loops and multiple edges are allowed. With vertices V1, V2, Vn, the sequence of degrees is called the degree sequence of G. Show that a sequence D1, D2, Dn of non-negative integers is a degree sequence of some graph if and only if the sum of these numbers is even. On one side, we already have it, because if there is a graph with this degree sequence, then the sum, we know by a theorem that the sum of all degrees is twice the number of edges, so necessarily an even number. What we have to prove is that if we have such a sequence and the sum of all of these numbers is even, then there exists a graph with that degree sequence, okay? Not all sequences respecting some even sum is a degree sequence of a simple graph. As we can see here, okay? These are two examples. We discussed that last time. These are two examples of sequences which have even sum, but, and I promise, they are surely degree sequences of a graph of several graphs, but at least one graph, but which is surely not simple. Okay? So what we have to do is this. If I have an input of n non-negative integers whose sum is even, can you give me a way to produce a graph which has that as degree sequence? Is there any, I heard some noise, maybe there is somebody wanting to give a solution?
Excuse me, Professor. May I have some solution for it, but I don't know how. Is my proof is really good for it? Can I tell it?
Sure.
I said that regarding to the theorem number 1.1 and its corollary, corollary number 121.
Oh,
Is
don't-
it in
it's later. Oh, yeah, probably, sorry.
is near the question?
This one?
Yes, yes. And the corollary number 1.1, which said in any graph the number of vertices of the odd degree is given. So
Mm-hmm.
if there is a proof under that, and if we understood this proof, and we can say that if the number of vertices of degree is even, so obvious that the number of even degrees is, I mean, the sum of them is even too. So
No, no, sorry. This is the previous one which asserts that. You don't need this one. It's directly from here. Necessarily,
yes,
the sum of all must be even. Yes, but this just proves one way. If there is a graph with that with a certain degree sequence, then the sum of all the degrees is even. The difficult part is another one. If you have a sequence, a finite sequence of non-negative integers, such that you have even sum, then there exists a graph with that degree sequence. This is the difficult part. Okay? Remember, the big difference between A implies B and B implies A. Here we have very clearly, as you are saying, that this is a degree sequence of a graph, then the sum is even. But can you prove that if the sum of these numbers is even, then there is a graph with that? For instance, but just as an example, if I give you this sequence, can you produce a graph with that sequence of degrees?
No, of course not, because it has 7 vertices that so
Oh, my friend, please
one, two,
be careful. There is a difference between simple graph and graph. A simple graph has no multiple edges, has no loops, and here this part is relative to simple graphs. Simple graphs. Whereas the exercise before is for a graph without the condition of being simple. So surely there is no simple graph having these degrees for its vertices. I swear that there is a graph which has this sequence of degrees, but surely it is not a simple graph. But mind, it's not enough to give me an answer for this sequence. I want you to produce a way of building a graph, whatever the sequence, the finite sequence of non-negative integers with the even sum is given, okay? But as I said,
no.
it is very important to understand the problems. Then you understand the solution. But if you see immediately the solution, you will not understand the problem. I want you to understand the problem. Is the problem now clearer?
Roughly speaking, honestly speaking, I didn't catch what you said,
Okay.
but the point you concentrate on it.
Okay, let me repeat it very briefly. Here you see, and the last time it was proved by some of you, that it is not possible to find a simple graph with these degrees for the vertices, and also none with these degrees for degrees of the vertices, even if this sum is even and this sum is even. Okay? Now,
Sure.
okay. So we all agree about this. Let's move to the other problem, which has not the constraint that the graph is simple. So we allow loops, we allow multiple edges. Now,
Uh-huh.
okay, now I tell you, if you give me such a sequence, if you give me such a sequence, I'll produce a graph, necessarily not a simple graph, which has these degrees for its vertices. But it's not enough to get it for these two. This can be a good way for starting, as I repeated this also for the nth time. Doing mathematics, solving problems, goes through trials, experiments, wrong, and maybe once right, okay? Experiments can give you the idea for the general construction. And what I suggest, and so I'll not now solve this, I'll solve it again next time. Now, I hope that everybody has understood the true meaning of this exercise. And so I suggest start by trying to find a graph having this and a graph having this as degree sequences. And then, out of that, try to get the general rule, something for which you could program a computer. I think you all are engineers, all of you have written some code, and you know what it means to write a code. It means that you must accept any input in a given format, and you must be able, and the computer must be directed by your instructions to produce an output with some constraints. The constraints here are clear, and the output requested here is clear. So start from solving these two problems, and what is important, get a general solution for this problem. Input any finite sequence of non-negative integers whose sum is even output a graph which has this as degree sequence. Next time I'll start solving it, okay? No more asking you, and because I hope that all of you devote 10 minutes. You understand, my friend, or the friend of 2 hours? No, 10 minutes thinking of how to do this. The important thing is to understand the problem. And here we have just seen that the problem was not so clear to understand, okay? Now I hope everybody has understood the problem. You have not understood, write to me, and we'll talk about that by mail. We had, we had 2 more problems. One was this, and this requires, as far as I know, a proof by induction, which is not particularly easy, and so I'll start it. I don't investigate whether you have tried or not, but this is much less amusing, so to say. Okay. Okay, so A adjacency matrix of a certain graph G claim in the case power of matrix A, power meaning that you multiply A by itself n times through the normal row by column multiplication. And let's give a name to this elements, call them Bij, the elements of this matrix. Bij is the number of K walks from Vi and to Vj. Okay, this is my claim. All right? So now I start the proof by induction. You don't remember what it is? Go back to the last lecture, no, the last but one lecture, where I said in general what a proof by induction is. Okay? Inductive premise. K equal to 1. One walk is a sequence U, E, V, where E is an edge between U and V. Then A is Actually, the matrix giving Aij as the number of one walks from Vi to Vj. So no problem for the inductive premise. Inductive step. And please, let me do it for simple graphs. But easily adaptable for any graph. Inductive hypothesis. A raised to h minus 1 equal, let's call it the matrix of Cij, is the matrix. No, let me write it more explicitly. Has Cij as the number of h minus 1 walks from Vi to Vj. Inductive thesis. Same thing with the h instead of h minus 1. AH equal, let's call it Dij, has Dij as the number of h walks from Vi to Vj. Okay. I hope you have written down. Anyway, remember that everything right here stays remains in the page of the program as a PDF. Okay. So now let's consider all possible H walks. Okay. Every H walk from Vi to Vj is so built. The I Let's do that. An h minus 1 walk W S from V I. I'm sorry, that's not right. Well, from VI to VS followed by the edge VS Vj if that edge exists. Okay? So, in other words, let's take any h walk from Vi to Vj. Take the last edge of this walk, okay? And look at the of the piece immediately before. It is an h minus 1 walk from Vi to some vertex. One of the vertices which has an edge from it, let's call it Vs, for which there exists an edge from Vs to Vj. Okay? All right. And how many walks do we have? We have as many h minus 1 walks we have from Vi to Vs, okay? So, the number of h walks from Vi to Vj is equal to number of walks from Vi to V1 to V1 if an edge from V1 from Vi to V1 exists, okay? If let's write it, if an edge between Vi and V1 exists, that is, if what happens if we have that an edge between Vi and V1 exists? If AI1 is equal to 1, different from 0 is important in the general case. Let's say here equal to 1, plus the number of walks from Vi to V2 if AI2 is equal to 1 plus the number of walks from VI to the knee if AI knee is equal to 1. But then what is this equal to? It is equal to what? By inductive hypothesis, what is our inductive hypothesis? Our inductive hypothesis is that the matrix A raised to H minus 1 having Cij as elements has this element which exactly counts the number of H minus 1 walks from Vi to Vj. So here I have the number of walks, and these are H minus 1 walks. H minus 1 walks. H minus 1 walks. H minus 1 walks, sorry. From Vi to V1, okay? And so this is what? It is equal to Ci1, element Ci1 of the matrix A raised to H minus 1. Okay, Ci1. We have to count it only if AI1 is equal to 1. We don't count it if it is equal to 0. And so this is equal to what? It is equal to Ci1 times A1J plus Ci2 times A2J plus Ci ni times A ni J. But this is exactly the element Dij of A raised to the H. Okay? All of you have understood? Okay? So, a first rather heavy use of induction, okay? If you want, next time I'll give you an example with a true graph, but you should try with the true graph and try with a to the third and to a squared and a to the third to understand everything what I've said on a concrete graph. But the proof is complete and formally untouchable here as it is. And so we have this, okay? Oh, well, what is this? Oh, okay, all right, so go here. I think if we had distance, we already did. No, I thought we had another one, a fourth one. This we have done. This over path of length k we have done. No, it's all. Okay, so, all right. So we'll go on with the cycles after a 10 minutes break. 1804, 05, 1815, we start again. Okay.